exercise 8, we've got this really cool thing called splitting. And yes, I'm a geek that I consider scripting cool, but it really gives you a lot of capabilities. Let me make that a little bit bigger. Get rid of the tools. So what we're doing here is, this is kind of building up on lists. We've got model new. We're creating a 20 by 20 model, going to be elastic. We're giving it some properties. And we're essentially applying a 0 velocity at the base, which is 0, 0 at this case. So we're just fixing the base. We're going to define a group based on grid points. So zone grid point group is we're going to call it surface, so it'll be the top of the model. It's just a box model. And we're essentially going to say any grid point that's along position Y equals 20, top of the model, we're going to associate that with the group called surface. And we'll see that in a minute, why we're doing that. And there's all sorts of reasons you might want to do it, probably around boundary conditions or being able to apply forces or something. But then we're going to turn gravity on, model gravity 9.81. And then we're going to use this really nice command called zone initialize stresses. So what it's going to do is, we've specified a density of 2750. You know how big it is, and it's just going to go zone by zone. It's going to say, well, I'm at the top, there's nothing above me. So based on the centroid of that zone, that'll be my depth. I know the density, so what's the stress going to be given no other information about stresses? So it's just a really good way to get your initial stress state very quickly. In the old days, you had to actually calculate it. Now it's just automatic. And then, of course, it'll do that same thing at the base. And it is based at the centroid of the zone. Let's run that little bit first. Oh, and sorry, I also want to include model save initial. So this will be the initial stress state. So I'm going to run that. Okay, so now we've got an initial model. And the reason I'm going to do that is I'm going to do some stuff, but then we're going to go back to that state and do some more stuff. So let's split model. Oops, sorry. I prefer it to split to the right myself. And we're going to do a new plot. In my case, it's plot 4. We're going to add a zone. And let's get rid of the project space so you can see a little better. Okay, so I can read the legend. So let's look at stress. So I'm going to do, I added a zone group plot item. I'm going to do contour. And I'm going to, for the zone value of contour, I'm going to look for stress. I'm going to change the quantity to be YY, so that's vertical. And so we can see here what we might expect, just a nice radiated stress field based purely on the density of the model and its size. Okay. So what can we do? Oh, and one thing to note. So just note that this is negative 1.35 times 10 to the 4. So the 10 to the 4 is the important bit. So with splitting, we use this new thing, this new symbol, which is just a double colon. And when we do that, what splitting lets us do essentially is it's a really compact, fast, efficient form of looping. So instead of doing like a loop for all the zones in a container, we can use that same zone list or structural element list or whatever. So that's the list of all our zones in the model. And what this essentially indicates is that we're going to do splitting. So I think the easiest way to think of it is a loop. It's a really compact loop. We're going to loop through all those zones in that zone list. We can also do this for any other list that we've created. If you've got a list with a well, a million numbers, you can navigate through that as well. And so both these lines 17, 18 more or less do the same thing, although this is an order of magnitude difference in what it's going to do. But we've got this intrinsic value for each zone called zone stress. But of course, there's XX, YY, ZZ, well, not in 2D, or it could be XY. So we've got to specify what component of stress are we interested in. And that's where this arrow operator, YY, comes into play. So we're interested in the vertical stress component of the zone, of the stress of all the zones. And what are we going to do? We're going to multiply that value by 10. So we haven't cycled. So I mean, if we do this and then we actually solve it, it's going to go back into equilibrium and reset everything. But let's run that. So the plotting doesn't change because it's sort of all relative. But if I zoom in, you hopefully can see that's now 10 to the 5. The second line does the same, it's the same idea, just does it in a different way. If you don't like this arrow thing, this arrow operator, the zone stress has an intrinsic YY, XX, XY component built into it. So we can simply do zone.stress dot the YY component for all the zones in that list, and we're going to times it by the value that is there now by 100. So if we do that, we are now up here. So it's 10 to the 7. So it went up 2 orders of magnitude. And so with splitting very quickly, I mean, it's a small model, so if you could loop through it, it would probably take just as long. But when you start imagining when you're working on real projects and you've got hundreds of thousands of zones or millions, or a 60 million zone model for whatever reason, which isn't that unusual in 3D, it might be a little tricky, unusual in 2D. But now all of a sudden, very quickly and very compactly, you don't need 10 lines of code. You can loop through it. It does take a little bit if you're not used to sort of using lists in Python or other programs. I know it took me a while to wrap my head around it, because sometimes you look at an example and there's like a double colon here, but not here. You just have to think of wherever you've got a list of something or a sequence of numbers that you want to loop through, that's where that double colon becomes important. So in this case, we're just timesing everything by some magnitude or some value. So this is a one thing, whereas this is a number of things, a list of things. So that's why we have this here. If we want to do something a little different, so now in this example, we're actually going to mess with the grid point positions. So we can say I want to query the position of the grid points. And to do that, I have to go through the grid point list. So I've got this double colon that indicates that I'm splitting. Again, just a really compact way to loop through the list. And for all the Y positions of the grid point position, I want to add a random number. So let's break this down. For one thing, we need this because we're not adding one number to the list or multiplying the list by one number. We're going to have as many random numbers as there are objects in the list. So really, it is a list of numbers. We're using the random generator, uniform random generator that we saw before. And in this case, this whole thing is just one number. So we don't have a double colon here, even though we're not looping through the list per se. We're trying to get the size of the list. So list.size of any list could be Fred, if Fred is a list. In this case is the grid point list. It's going to give us a size. So I don't know what it is. Maybe it's 1,000 grid points. So now it's going to generate 1,000 random numbers, and add that value to each grid point position. And you almost have to kind of sit down and go through these yourself to, I think, get a good sense of it. I know I did. And then I made a couple examples, and in doing that, that really helped in my own mind. Right. So now when we look at that, and I can't guarantee that this is a good mesh anymore because things might have crossed over each other. So it might explode if you try to cycle it, but you could imagine if you, maybe you could put limits or do a test afterwards and adjust things. But really quickly, you can do that. And then I'm going to restore, bring the project space up. I'm going to go back to the initial state. So we've got our stresses there, but we didn't muck up the grid points. And I'm going to turn off the project. And then now I just want to do that just for the surface. So I want to add some random topography to the surface. How do we do that? So these split things are really good if you've got a list. But how do you do part of the list? So the trick there is you make another list. So surface, which is the same name that I gave to that grouping of grid points that we earlier defined through a command. I'm going to say surface equals grid point list. So it's going to look at all the grid points. But then we're going to test it. There's an intrinsic called isGroup. We've got that for grid points, for functions, for struct, everything has, or pretty much everything has it. Do you belong to this group? And so we're basically going to say of the grid point list, and I'm going to look for surface. So if surface is any grouping of that grid point, it's going to add it to the new list called surface. And so it should just pick the guys at the top. I mean, if we had called this group up here Fred, we would be searching for the group called Fred down here. When we run that, so first of all, run that, nothing's changed, but we just created a new list. So if I was to look over here, fish global symbols, I've now got surface with 21 items in it. So I would bet you there are 21 grid points on top there. Turn that off. So now we want to do the same thing that we did before, but instead of using the whole grid point list, we're just going to use this surface list that we just created. And when we run that, sure enough, it's just limited to the top here. Okay. We can initialize the stresses just to make sure everything's reflects now the fact that it's no longer flat. And then I'm running out of time. So just really quickly, I'm going to run this example where I've now assigned a random extra variable, just like we had done in that simpler model. Before, I've assigned a random variable to each extra. I'm not plotting extra variables, so nothing's changed. But now I'm going to multiply the extra variable by the stress that's in those zones, and it becomes a little more random. There's no real reason why you might want to do that, but it's just another example of how you can interact with these lists and using splitting. So let me pull up the project. I'm going to leave this example for you. That's what I did with FLAC2D. It's just an example to create a model that has a custom modulus distribution, and it's based on an equation. Equation doesn't matter. These are material constants that just have a fixed value. What it's doing is it's changing the Young's modulus, I think, based on the depth. So this modulus is increasing with depth. And so start you off with like how to build the model. But if you look here, this is how you could solve that problem using loop for each, which is a very common way to do it. Most of our consultants are probably still doing it this way. But there's also down here, these last few lines is how you could do it with a list and with splitting. So take a look at this and try that yourself. And then the last thing I'll talk about just really briefly is why that might be desirable. And I had this example in 3D on our website, and so I've made a 2D version of this. But the idea here is you're going to loop through all the zones and randomly assign a value to the UCS, like the 30 plus or minus 10 kind of thing. And what you'll see when you plot that is this kind of random distribution. If you do it with a loop while, it's like 44 with a for each, it's 22. These are actually hundredths of a second, so it's pretty fast however you're doing it. But say your model took 41 days. Using for each, it would take 22 days. Splitting, 11 days. And I'm not going to get into it, but it is in the example on the next page. An operator is something that I encourage you if you're doing really big models or querying fish as you're cycling, doing stuff. Look at operators, because that's 1.2 times 10 to the negative 5. So really, really fast. And then this example is on the next slide. And it's also in your project folder called loop splitting operators. So that is that. Crash course in fish.